Now that we've reviewed some general chemistry concepts of bonding and structure and learned how to draw molecules and how to predict information they might contain, it's time to finally start talking about reactions. And when we're working with hydrocarbons, alkanes in particular, there aren't very many reactions that occur. There are, in fact, 3 types of reactions of alkanes of commercial importance. One of these you've already studied, and that's combustion, which you recall is the reaction of a hydrocarbon with oxygen to produce CO2 and water. This is the most commercially important reaction of alkanes because it's the one that provides the largest quantity of energy for use. And you remember how to balance the combustion reaction. If we have methane gas reacting with oxygen to form CO2 gas and water vapor, we'll first balance carbon, which in this case is balanced because methane contains only 1 carbon. Then we'll balance hydrogen, 4 hydrogens here, we require 2 waters. And finally, we will add the coefficient in front of oxygen that's necessary. We have 2 oxygens here and 2 more there. That's 4 oxygens. We need 2 O2 molecules. At this point, everything should be balanced. You'll notice that in this particular case, we start with 3 molecules of gas, and we end up with 3 molecules of gas. So there's no particular entropy advantage. But this does generate a very large amount of energy, which heats up the gaseous products and causes energy to be available both in heat and in pressure. As you go up to higher molecular weight alkanes, C2H6 for example, products again, CO2 and water vapor. This time we need a coefficient of 2 in front of the CO2, and we've got 6 hydrogens, which means we need 3 waters. And so now we have 2 O2 molecules here, and a 3 halves O2 molecule there. So we need a total of 5 halves O2. Sorry, 7 halves O2. Right? We have 4, 5, 6, 7 oxygens over here. 7 oxygens on this side. If we want to avoid the fractional coefficient, we'll multiply everything by 2. C2H6, 7 oxygens. CO2, 6H2O. And you'll notice we start with 9 molecules of gas, and we end up with 10 molecules of gas. Typically, we do end up with a slightly larger number of molecules of gas on the product side than the reactant side, and therefore a entropically favorable reaction as well as an enthalpically favorable reaction. And you'll notice anytime you have an even number of carbons, you end up with a fractional coefficient in front of your oxygen that requires you to multiply through by 2 if you'd like to avoid those fractional coefficients. And we can keep going. So this reaction is not of interest to an organic chemist because it actually takes more complex structures and makes them into simpler structures. And we are usually trying to create more complex structures. From simpler structures, carbon dioxide is not a particularly useful feedstock in the laboratory, chemistry laboratory, although industrially it can be sometimes used. And we will see some examples of using CO2 as a source of carbon organic molecules, but not very many. So this reaction, although it's the most important commercially, because it's our energy generating reaction, is of no real interest to chemists. The second reaction is also of no particular interest to chemists, except that it is the reaction that takes raw petroleum and creates smaller molecules that can be used as feedstocks for our for organic chemistry and that is pyrolysis. Pyrolysis, pyro heat, lysis cleavage. This reaction involves heating a mixture of long chain hydrocarbons strongly to produce shorter chain hydrocarbons. Petroleum is a complicated mixture of long chain hydrocarbons, and through the process of pyrolysis, we can convert crude oil into useful products that have reasonable boiling points. What we're going to do is we're going to take a mixture of a smaller number of shorter chain hydrocarbons and then use distillation to separate those hydrocarbons by boiling point into useful fractions. The smaller the molecular weight, the higher the fuel value, which means that you can generate more energy per gram of material. The fuel value is defined as kilojoules of energy released per gram of starting material. And they also burn more cleanly, so you're less likely to get incomplete combustion products like carbon monoxide out. So the process is quite simple. One takes a hydrocarbon, use pentane as an example, although pentane is actually a product of pyrolysis commercially more than starting material. Starting materials are much longer, and we heat it up. And if you heat it enough, you can start getting bond dissociation. And those bonds will break homolytically, which means that to form radicals. And free radicals are compounds that have an unpaired And you'll see that on the right-hand side of the board, I've reproduced table 3.2 from your textbook that has carbon-hydrogen bond dissociation energies for a variety of carbon-hydrogen bonds and carbon-carbon bond dissociation energies for a variety of carbon-carbon bonds. So we can see that, for example, for methane, breaking one of the 4 identical CH bonds takes 105 kilocalories per mole. For ethane, breaking one of those 6 identical primary carbon-hydrogen bonds takes 101 kilocalories per mole, and pretty much the same amount of energy for breaking one of the 6 identical carbon-hydrogen bonds on either propane or butane. If you're breaking one of the, or isobutane in this case, if you're breaking one of the primary carbon-hydrogen bonds, it's about 101 kilocalories per mole. If you break one of the methylene hydrogen bonds in propane, so breaking one of the CH bonds except the one on the end, it takes a little less, 98.5 kilocalories per mole. And if you have isobutane and you're breaking the tertiary carbon-hydrogen bond, still less, 96.5 kilograms per mole. And one of the things we will have to do at some point is address why that's true. Why does it take more energy to break a methyl CH bond than a primary CH bond, which takes more than a secondary CH bond, which takes more than the tertiary CH bond? What must be happening here is that the radical, since it's hydrogen on all cases, the carbon-based radical must be more stable as we go from methyl to primary to secondary to tertiary. That's due to a phenomenon known as hyperconjugation we'll talk about in a future video. If you look at the carbon-carbon bond dissociation energy, it probably comes to no surprise that those require less energy. The bonds are longer because they're between 2 second row elements and therefore longer, usually they're weaker, as opposed to the shorter carbon-hydrogen bonds. But still, we see the same trend. If you break the carbon-carbon bond in ethane, yielding 2 methyl radicals, it takes 90 kilocalories per mole. If you break the carbon-carbon bond in propane, creating a methyl radical on one side and a primary on the other side, a little less, 89. If you break the middle of butane, the CC bond neutral side, again, it takes a little less. A secondary radical on one side and a methyl on the other takes about the same, 88. A tertiary radical on one side, methyl on the other, 87. 2 secondary radicals, 85.5. 2 tertiary radicals, a little less, 78.5. This still reflects the fact that the tertiary radical is more stable than the secondary radical, and the secondary radical is more stable than the primary radical, and the primary radical is more stable than the methyl radical. But the thing to notice here is that even the strongest carbon-carbon bond in ethane is significantly weaker than the weakest carbon-hydrogen bond in isobutane. So if you start heating things up, the bond that's going to break first is the weakest bond, and that's always going to be a carbon-carbon bond. So the carbon-hydrogen bonds are largely untouched by the pyrolysis process in the initial stage. And what we do is we break a carbon-carbon bond. So we can break 2 different types of carbon-carbon bond here. If we break this one electron goes that way, 1 electron goes that way, and we use curved arrow notation with 1 arrowhead. This is 1 electron moving, and with 2 arrowheads, it's 2 electrons. We're working here with homolytic bond cleavage, so we're working with fish hooks where a single electron goes to each target. If we break that bond, we would generate a 4-carbon primary radical and a single carbon methyl radical. Alternatively, we could break this carbon-carbon bond between the 2nd and 3rd carbon in the molecule, and if we did that, we would generate 2 different primary radicals, a propyl radical from one side, and a methyl radical from the other. It will cost us, since this is a primary radical on one side and a methyl radical on the other, approximately 89 kilocalories per mole to do that first step, and it will cost us, since it's primary on both sides and the other, approximately 88 kilocalories per mole to do that. Both of those numbers are significantly less than the 98.5 kilocalories per mole, which is what it would cost to break the weakest of the carbon-hydrogen bonds in this system. Sorry, 101 kilocalories per mole, right? So we're going to break carbon-carbon bonds, and we're going to have 4 different radicals in the solution. We will have methyl radical, propyl radical, and butyl radical. Those radicals can now participate in one of 2 different processes. To create new hydrocarbons. The first process is radical recombination, where 2 radicals will react with each other. And the second process is hydrogen abstraction, where one of the radicals will pluck a hydrogen off the position adjacent to the radical in another one. And I'll illustrate that with a few different examples. Radical recombination. 2 carbon radicals. Combine to make a new CC bond. have 4 radicals in solution, so we have a lot of possible radical recombinations. We can take a CH3 radical and react it with a CH3CH2 radical to make propane. Creating this new carbon-carbon bond by the combination of these two. Or we can take 2 CH3 radicals and they would combine to make ethane. Or we could take a CH3 radical and a propyl radical. That would combine to make butane. I think you can see that there are a large number of different possibilities since there are 4 different radicals and they can combine in any binary pair. It's possible to make larger hydrocarbons. You have the butyl radical present. It would be possible for the 2 butyl radicals to combine to make octane. And I'll shorthand that so I don't have to write all the CH2 groups out, there'll be 6 of them. But if you keep this reaction going for long enough, the tendency is to go away from large hydrocarbons towards smaller hydrocarbons because entropy will favor the larger number of small hydrocarbons over the smaller number of large hydrocarbons. And once you have octane, the 2 carbon-carbon bonds that you can break in there cost 89 and 88 kilocalories per mole respectively, and you can keep breaking them up into smaller units. So the tendency will be towards the larger number, the smaller hydrocarbons. That's radical recombination. It's simply a bond reforming from the opposite process of the original bond breaking. The second process that's possible is what we refer to as hydrogen abstraction. And in hydrogen abstraction, a carbon radical pulls off a hydrogen adjacent to a second radical, carbon radical. Produce an alkane and an alkene. So we make carbon-carbon double bonds here. It has to be a hydrogen adjacent to the other radical so that the electron being released from that can join with the other radical to form that double bond. So, for example, a CH3 radical would interact with an ethyl radical by removing one of these hydrogens from the adjacent carbon. Form a new carbon-hydrogen bond and release the second electron to combine with the radical on the second carbon. And the product of this would be ethane and ethene. This is also known as ethylene, the common name ethylene, the IUPAC name ethene. Lots of possible hydrogen abstraction reactions are also available. For example, react a propyl radical with another propyl radical. extraction, it would have to be one of these two hydrogens that's removed, not one of these three or one of these two. It has to be on the adjacent position. Often we will label those with Greek letters, alpha being the carbon right where the reference point is, in this case, the carbon containing the radical, and then the beta carbon is the next one, the gamma carbon is the next one. So it's not an alpha carbon or hydrogen that's removed, it's not a gamma hydrogen that's removed, it's one of the beta hydrogens. Pull that off, form a new carbon-hydrogen bond, and release the second electron, form a new carbon-carbon bond, and the product will be propane and propene. Also called propylene. Propene is the IUPAC name, propylene is the common name. The polymers produced from these take the common name. So the polymer derived from ethene would be polyethylene, and the polymer derived from propene would be polypropylene. You're probably familiar with both of those. Polypropylene is number 5 on the recycling scale. High density polyethylene is number 2, and low density polyethylene is number 4. So you've seen a lot of products produced from the polymers derived from ethylene and propylene. In the old days, ethylene and propylene were not considered to be useful products, and they were simply burned off during the petroleum refining process in favor of the liquid products, things like pentane and hexane, and some of the smaller gaseous products like butane. But now, those materials are recovered and used to make plastics. So radical recombination, two carbon radicals coming together to make a new CC bond, hydrogen abstraction, the radical plucks off a hydrogen to form a new CH bond, releasing a kind of a second radical, and then those two adjacent radicals combine to form a carbon-carbon double bond. You'll get from refining of petroleum by pyrolysis a large, complicated mixture of fairly small hydrocarbons. Between 1 and maybe 8 isooctane is a common constituent of gasoline, and it's an 8-carbon unit. And then by fractional distillation, using really long distillation columns, we'll separate the different cuts into jet fuel and kerosene and regular gasoline for automobiles and creosote at the end and various higher molecular weight lubricating oils and things. It's a very important reaction, but it's not a useful reaction in terms of generating things that are good for organic chemistry, because what we're generating is alkanes, and the alkanes don't have any polar bonds in them, which means that they're not really reactive towards most reaction conditions. The third reaction, and the important one from the perspective of organic chemists, does introduce a polar bond, and it results from the reaction of a hydrocarbon with a halogen. The halogen-halogen bonds are all significantly weaker than carbon-carbon and carbon-hydrogen bonds, because the halogens are large atoms, or in the case of fluorine, there's a lot of nuclear compulsion. So the third reaction, the one that's going to be the subject of most of our discussion of this chapter, chapter 3, is free radical halogenation. And free radical halogenation takes a hydrocarbon, reacts it with a halogen, diatomic chlorine gas in this case, to produce a haloalkane, and a hydrogen halide. So in this case, ethane reacts with chlorine to produce chloroethane and hydrogen chloride. Instead of putting in energy thermally, delta for heat. We put in the energy using UV light, and we use H nu for that Planck's relationship that says that energy is equal to Planck's constant times the frequency of light. So when you see H nu, that implies that we're adding radiant energy, light energy, instead of heat energy. In the next video, we'll address the mechanism for this reaction of free radical halogenation.